Alright, Mr. Claxton's Algebra 2 students, if you're watching this, then you have found a means by which to view the video that I left for you today. I know I'm gone. I left a message for the seniors and a message for the underclassmen. I hope you get that as well. Now, this video is going to address the learning objectives, or what I want you to know, 1, 3, 6, and 7. We have addressed 2, 4, and 5 in previous lessons throughout the week. Those are just there to kind of keep you on track, so you can you make sure you're not going to be falling behind, or to make sure that you know what's going to be on the quiz Tuesday. So let's go ahead and start with an explicit formula, right? An explicit formula is really important to our well-being when considering arithmetic sequences. We want that general formula. So what is the explicit formula for the example that I have listed here? Well, if you take a look, we've got 9, 13, 17, 21, 25, 29. We have to determine what the constant difference is. That's very important. We are going up here, and we're going up the same amount each time. So if you take a look from 9 to 13, some people might have to type in 13 minus 9 into their calculator. Either way, you're going to get plus 4, 13 to 17, plus 4, 17 to 21, and I always check them all, plus 4, 21 to 25, absolutely, and Yahtzee, got it. So because that does stay plus 4 throughout the entire sequence, we know it's an arithmetic sequence, but we're really not extremely concerned about that right now. We just want the explicit formula. Couple different ways to write the explicit formula. You might start off with a really general, and general is the formula that I gave. I know I gave fifth period the other day, where we're going to take n minus 1, and we're going to multiply that by the constant difference. Or the common difference, as the book calls it sometimes. And we must remember that starting value in there. Where do we start at? So we take the start value and add it to that. Now, I like to simplify it down even a little more than that, but for the most part, if you know this formula, you can write a general or an explicit formula. General form, an explicit formula. In this case, all you have to do is follow directions. You take the 9, and then we're going to keep that n minus 1. That n minus 1 just means the term before. So n minus 1. And we know our common difference is 4 times 4. So, I could say that, t with respect to n. And that's just in function form. T with respect to n. I could also call that t sub n as 9 plus n minus 1 times 4. And I could find the 100th term. I could find the 1000th term. I like to keep going with this. I like to call it a linear, the linear form of the function. So the linear form of this function, if we distribute that 4 through, is going to be t of n set equal to 9 plus 4n minus 4. And you're going to see some like terms there. 9 plus 4n minus 4. Well, what are the like terms? Like terms are the constants. So we take 9 minus 4, and we can rewrite that. Now, I call this the linear function of that, because if we wanted to graph a line of the data that this series, or the sequence 9, 13, 17, 21, 25, 29 was spitting out. If we wanted to graph that, we can graph that as a line. And I really like this because you can write it in slope-intercept form. Oh, how I love these slope-intercept form. And then plus 5. And you could go ahead and check that. The 100th term, if you'd plug 100 into here and take 99 times 4 and add 9, that's going to be the exact same as 100 times 4 and then plus 5, so 405. Moving on now, you must know how to declare the explicit formula, because that's going to help us to find what the last term of a series is. Because right now, in 11.3, we're talking about arithmetic series. So arithmetic series, and that is kind of a big question on the day. A big question that you will need to answer at some point is, what is the difference, as I move down here, what is the difference, whoop, that was I got ahead of myself. The difference between an arithmetic sequence and an arithmetic series. So what is the difference there? Basically, what you're going to come to find is a sequence is the list of numbers. The series is the sum of that list. So series is the sum. Okay? The sequence is just a list of numbers. So moving back up the line here. All right. So the reason why we need this skill, and that's kind of like a review skill, which I'm not going to take you through the second example I had. I had a second example to try. I think you're going to be able to do that. If you wanted to see a second example, I'll go ahead and show you this one real quick. This is the example I was going to show you anyway. So what I started with was 12, 7, 2, negative 3, and negative 8. And at that point, I would call 12 my first term. I call 12 my first term, T sub 1. T sub 1 of the sequence, right? Now, after I ran the same process that I just showed you, meaning that's the recursive form. We don't want to mess with that right now. That's just the recursive form, a different way to write it. We start with, by using that formula, the start value 12 plus n minus 1 times the constant difference of negative 5. So after I run that through, okay, and I kind of test it out here, t at 100. After I run that through, so I'm going right over here now. I know the order might be kind of messed up. I get that is the same as negative 5n plus 17. Now, notice that positive 17 would have been my t sub 0. This t sub 0 here, and I can get t sub 0 by following the pattern backwards. You might know that the pattern backwards is adding 5. So adding 5, you would get 17. And notice that 17 is like my y-intercept. So some people look at this as a much faster way to write that explicit formula, that general, the linear function form. You know, and looking back at what we did here, we would have just had to follow this back 4. So if I go back 4, I know t sub 0. T sub 0 would be, I know you're thinking it, okay? I would just, as I would subtract 4 from that. Oh yeah, duh, Mr. Claxton, it'd be 5. Absolutely. Yep, and it was 5 over here, and I know my common difference. So that sometimes jives with people. It's a little more common to what we've done in class. So let's put this all together now. Understand that I am assuming that you have completed the lesson opener. So you've talked about an arithmetic series and what that is. An arithmetic series, remember, is the sum, and this is a common problem that's presented in mathematics for arithmetic series. We're always stacking cans. I love to stack cans all the time. It's really fun. Well, sorry, I just said that. All right. So I'm hoping that you did run through the lesson opener. You should have noticed in number 6, it was a key question, that, yeah, they were all 7. In exercises 3 through 5, they were all equivalent. They were all 7. And, finding the sum of the integers of 1 through 6 is the same as multiplying 3 times 7. Well, how about that? 3 times 7. So we had half the number of terms there. Okay, at 3, half the number of terms. And then the sum of the first term and last term was 7 each time. So 3 times 7, the sum of those terms, right, yes, the sum of those terms is 21. All right, so the first 15 counting numbers. Well, when we have the first 15 counting numbers, using the same method, you might say, well, I know that the sum of my first term and last term, and by counting numbers, it means like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the sum of my first term and my last term is 16. So my first term and my last term, that sum is 16. And then half of the number of terms that I have is 7.5. Whoa, 7.5. So the sum of the first and last term is right there. Perhaps I should have written this in blue and that in pink. And then the average, or the number of terms I have divided by 2 would be 7.5. So, I mean, either way, let's see here. Oh boy. That'd be 120. So we can see that, you know, 120, first 15 counting numbers. Now, really, what we're trying to guide you to is that the general formula, for the general formula, you multiply the average of the first and the last terms by the number of terms. That really doesn't match up real well with number 8 and number 7 and what you were thinking, but that does match up with the formula, the sum of the first n terms of an arithmetic sequence, that formula, right? So that formula is S sub n, and S sub n is just the sum of the first n terms. Is n times the average, that's in green right there, the average of the first and last term added together. So that's the first term plus the last term divided by 2. Now we could have done the same thing back here and gotten 120. Okay, we could have taken 1 plus 15, which is 16, divided by 2, which is 8, and multiplied that by 15, and we would have gotten the same number. There's different ways to get to Grandma's house. I hope that you've learned that at some point this year. So we can apply this formula anytime that we're given the terms. It's really easy, and given the term number that we're going to, you do need to have that defined. You need to know how many terms you're finding the sum of in order to find the sum of an arithmetic series, or to find an arithmetic series. So in this example right here, they give us the general formula and want us to find the sum of the first 17. The sum of the first 17 terms of that sequence. So what I have to do is I have to use that formula to figure out the first term and the last term. So use the formula, figure out the first term is 8, 6 times 1 plus 2, and then the last term, 6 times 17 plus 2. Now we got 60 plus 42 is 102, and 104, right? 104. And that's really all you need. You can apply the formula from there. Take 8, add 104 to it. 8, and I'm running out of my time here. I wanted to make this definitely less than 15 minutes. I know that you're probably getting bored. I'm going to go ahead and pause it and come right back. Alright, and we're back. As you can see there, I took the number of terms, which was 17. There's 17 terms, T1, T2, T3, so on and so forth, all the way through 17. Term 1, term 2, term 3, that's what that means. I took the first term, 8, added 104 to it, divided that by 2. I know that value is 56. When multiplied by 17 gives us 952. So S sub 17 is 952. That's the sum of the arithmetic series through 17 terms. is 952. You know, looking at something like this, this problem is a little more difficult in that it only gives you the first term, second term, and the third term. So we've got t sub 1 there, t sub 2, term 2, term 3, and term 4. It wants to sum the first 11 terms. Now, I know a lot of you are going to take this out to 11 terms. You're going to figure that out, figure out what's happening there every time. You're probably seeing it right now. Oh, minus 4. Yeah, I'm subtracting 4 every time. Absolutely. Yes, you are. So subtracting 4 every time, that is going to be our common difference. Is going to be negative 4. You'll notice here that I need to figure out the first term and the 11th term, and I know that some of you would already be to the 11th term. I'm just going to go ahead and pause real quick and come back with that first term and 11th term. Now, in order to get to the 11th term, I do have to use the explicit formula. So I'm going to go ahead and just, it's going to be a stretch for some of you. I know that my constant difference is negative 4. I'm going to take negative 4, and I would multiply that by n. Okay, in this case, n is 11. So, I mean, the general would be negative 4 times n. In this case, n is 11. And we're going to add that to t sub 0. Now, t sub 0, if you remember me talking about t sub 0 earlier in this video, t sub 0, remember I would need to add 4 in order to get back, in order to keep that constant difference the same. T sub 0 is going to be, I know you're thinking it, 20. So I know that my 11th term is going to be negative 44 plus 20, which is equal to negative 24. Negative 44 plus 20, right? All right, so as you can see, if we find the sum of the first 11 terms, what I did there is, after I found the first term and the 11th term, I added 16 plus negative 24 together to get negative 8, and divided that by 2. I just applied the formula, that special formula that we've discussed, the sum of the first n terms of an arithmetic series. You can call it an arithmetic series formula. Arithmetic series formula. All right, you know, given that information, we should be in control for completing pages 710 to 711. You know, I tried to keep it light there, light enough to where you might even be able to finish it. No homework over the weekend. Yay! Thank you for watching. You know, watch it again. You know, put it on while you're eating your Cheerios or Fruit Loops in the morning. Help me to get my views up. I thank you very much for being students of mathematics.